And thank you very much. And I guess this last table isn't needed if you want to put it back. Okay, thank you, people online and in the room. For the online people, it looks like I have to admit people, and I'm not sure if that message is going to keep popping up. So if any of you see something saying people need to be admitted, let me know. And I've also had this issue with the people in the room that the bar of attendees pops up once in a while. So if it pops up on that screen on my computer, let me know. Okay, good to see everyone. Last, for those of you who were here on Thursday, you heard a bit about AFNI as a whole. I'm going to focus on one aspect of how we think about fMRI, which is how we do quality assurance on data. And the two things I want to sort of start out with the title slide is this started out as my talk based on a paper that I led a few years ago. But as I was working on it, Catherine Walsh was actively collecting a data set, and I was like, hey, from that data set you're collecting, can you give me a good example of this, good example of this, good example of this? So at some point, about a third of the talk is great examples I got from Catherine. So I decided to add her name as an author here. So thank you, Catherine, for all that. The other thing I want to note is there's two terms that I am using interchangeably: quality assurance, which is sometimes abbreviated QA, and quality control, which is sometimes abbreviated QC. There might be people who are very opinionated on what the difference between these two terms are. Quality assurance is sometimes like protocols and systems, and quality control is sometimes like metrics and stuff. But I am pretty much using them interchangeably. And yeah, so just if you see, I tried to sort of be consistent in the presentation, but if you see them bouncing back and forth, I'm pretty much referring to the exact same thing. So I will note there are two main sources for this talk. One is this paper I published a few years ago, which was part of a special issue that a bunch of people all analyzed the same data set, and with the purpose of trying to demonstrate QC methods on the same data set. So I'm going to have some pictures from there and the overall framings from that paper. And then the other is what I just said. Catherine has an ongoing study. So far, the main output was poster at HBM with some early results. But if you want to see the poster and get more context to the study and where all these QC images came from, there's the info on that study. I am going to start with my take-home messages. That there's a lot of talk in the field about reproducibility. And my main message here is that reproducibility requires knowing your data. There's a lot of arguments out there about, like, which pipeline you use, how stable are your pipelines, how many subjects you need. None of that matters if you have bad data. And the other message with that is good data varies with context and applications. There's some things that I think everyone would look at and say that's bad. And there are some things that really depend on what you're using data for and what the context is. Quality assurance protocols are central to knowing your data. So it's not just, hey, if I remember, check this. It's as you're designing your study, thinking about what are you going to systematically test for as you collect your data. I should also mention that this is both for data you're collecting and for data that you're downloading. So a lot of downloaded data, I'll get to this a bit more, is we kind of assume someone looked at it, must be all good. That is not true. Pretty much any data set I've ever downloaded has some undocumented issues. So if sometimes even more, if you're downloading data, you should have a quality assurance protocol saying, okay, what am I checking in these data? Another key take-home message is automation is great, but insufficient. I'll show a lot of summary metrics and a lot of things, but a lot of this still comes down to a person sitting down and looking at the data. Overall, and this talk is part of it, training on quality assurance does need more attention. And quality assurance is not just sort of something we do, it's also an area of research that we're trying to improve. So you'll get a hint of, some things that exist. And at the end, I threw a few things in that are active areas of research. So overall, why focus on quality control? I think there's been some significant changes in the field in the last 5 or so years. The good changes, we have a lot more large sample size studies and a lot more shared data. So many more people have access to fMRI data. The neutral is different people design, collect, and pre-process and analyze data in different ways. So while one person might have thought of for the data and what one person thought was good data quality might be different from someone else. And the less good is people tend to make assumptions about data quality from previous phases. Especially with downloaded data, people just sort of say, hey, this is good, let me go for it. And the other reason to focus on is teaching is often a hands-on procedure. Like when someone new starts in the group, I could say run the script, but then they get brain images with blobs. And then looking at that and saying, this is the blob that looks good, and this is the blob that looks bad. At some level involves hands-on training. And understanding, that looks bad, but that's okay, or this looks okay, but it's actually bad. Actually involves hands-on training. And I think especially with the push towards online shared data and the fact that there are entire labs that have never collected data, I feel like some of that hands-on training is getting lost. So hopefully, this talk and others is one push against that trend. Any questions so far? Okay. Just to give you a sense of what I mean, I'm going to start with a mildly provocative case study. The Human Connectome Project is a massive N of 1,000 study that was conducted a bunch of years ago. And I've several times heard it referred to as sort of, we use the gold standard Human Connectome Project data. So I'm going to pick on that data. They're big, they can handle it. This is an arbitrary volunteer I picked from the HCP data. Literally, I saw a bunch of numbers. I opened up some random one that was at some point on my screen. If you look at the structural image, this is the fMRI data. It's 2 millimeter voxels. There's a lot of distortions. The brain is like really twisted. You can barely make out any gray-white contrast on it. Compare this to another shared data from this Abide autism study, and you can see that there's a lot of distortions. You can make out a decent, even though this is bigger voxels, this is 3 millimeter versus 2 millimeter, you're actually seeing more structure in the brain here. And I'll note that, like, if you look at the HCP processing pipeline, they've done all this stuff on distortion corrections, and they made a lot of innovations and methods improvement on distortion correction. One of the reasons they did that is because the raw data is very distorted, and they needed to innovate on distortion correction to make it useful. And now this is a temporal signal to noise map. So temporal signal to noise is just mean divided by standard deviation of the data. It's a good, quick and dirty metric to say how stable your data is. So like if you put a jar of oil into the scanner, you would expect not much variation over time versus the mean. In fMRI in this one, we're looking at the HCP. The temporal signal to noise at the highest is like 50 to 60 for most of the brain. And if you look at these areas in the center of the brain, it's like 20. Compared to the Abide data set, where almost everything is above 80 and often saturated close to 120. A TSMR of 20, like some of the people in this group, and I think we're gonna have some talks later on, are really pushing resolution to like sub-millimeter. And they're like, okay, 20 millimeter, TSNR 20 with a lot of data is unusable. TSNR 20 for like production fMRI is pretty bad. And we're seeing this in the center of this random data set I showed. So what does this mean? Context and applications matters. The HCP data set has now been used for many years. It's had many successes. What are those successes? Most of them are when you take regions of interest, you average data across multiple small voxels, increasing your signal quality, your averaging embedded and signal to noise. Correlation studies that average across the entire time series or averages across the entire population. We've had many great studies and methods development with this data. Where has the HCP fallen short? Studies that take full advantage of, they really push that short TR and small voxels. There are very few studies that really take advantage of both the short TR and small voxel without averaging in at least one of those. And the other thing that's fallen short is brain-wide association studies, which require robust and stable data in individual people. So if you're trying to say this individual, this metric compared to this one, HCP has not, as you know, there's actually a paper saying that, like, you know, you really need more data if your data is HCP quality to do it. So it's fallen short. And if you know if those QC scans are representative, that is part of why. I do want to note that I'm making an overly broad and not completely fair generalization on one study. Like I said, this is a massive study; they can take it, but it hopefully gets you thinking about, you know, what do we mean by good data and what matters. And especially just great data for one application may not be great for others. And you really got to view, and you have to understand what matters to your study and view those metrics. So as I'm approaching the rest of this talk, here are some just general questions building off that to think about. One is, if you're especially if you're collecting or downloading data, a key question is, will these data have the potential to accurately and effectively answer my scientific question? So that means knowing what your question is, knowing what metrics matter, and design and looking at measures that show that you're going to be able to get what you want. And if you want to stretch even more, like especially if you're acquiring data, if I do something a little bit more, if I test something, will it be useful for things I haven't thought of yet? Because it's always lovely to like have a data set for one purpose that ends up getting more uses. The other thing to keep in mind in general is identifying and logging anomalies or unexpected variations that might skew or hide key results. This is especially important with these larger studies, where a subtle thing that if you're not noticing, some things are just noise and make your data lower quality. Some things are biases, and identifying those and logging those, especially when you're sharing data. You know, if your notes say my subject fell asleep during run 3, it would be, you know, that impossible to tell unless someone logged if the subject fell asleep during run 3. Or if you've looked at your data and your subject didn't perform a task during one of the runs, don't leave it to your future self to remember to skip that run. You want to have some sort of log to share with your future self and others. The other key message I want to stress is all data sets have problems. If you don't check your data, you're going to get incorrect or misleading interpretations of results. If you check your data, you're going to have fewer problems. And that's the main thing. There's no perfect thing. We're always going to let things slip through. But if you're not checking, that just means you don't know you have no clue what's slipping through. I'll also mention for the paper that I wrote, one of the references that I really liked was a generic paper on QC in general from Wang and Strong in 1996. And they divided QC into what they called intrinsic and contextual measures. So intrinsic is a measure that's sort of, you know, we might have a different measure of like what's good or bad, but intrinsic is something inherent to the data. So like temporal signal to noise, the mean divided by the standard deviation, that's an intrinsic measure. Like you can collect any fMRI data, and that's a useful measure. And then there's contextual measures, which are, I am doing a study on decoding memory in the hippocampus. I want to make sure that the data in my hippocampus is really stable and good, and I don't really care what's happening in the frontal lobe of the brain. So those are contextual measures, and we very much have both in fMRI data. Any questions so far? So I do not expect you to read all the text on the slide. This is in a paper I mentioned. I have this list in the appendix. You go and look at this stuff and read it more carefully. This is sort of, I've divided a QA protocol into different sections. So there's general study planning, during acquisition, soon after acquisition, and during processing. And for the rest of this talk, I'm going to be going through examples in each of those sections. But this is sort of an expanded list beyond the examples I have here. The one thing I want to stress with this appendix, because I think it's a useful document, but it's not a checklist. It's not like, have I done step 1, step 2, step 3? It's questions. So each of these, it's, you know, which voxels have usable data? So your question is, where do I want usable data? Like, how do I care about that? How do I define usable? If there is additional measures, it's what you're collecting and what you're knowing. As far as like, what do you want to save and document? So this isn't a list of like save and document these, it's questions of thinking about what you're collecting, what you want to document. So I think this is a potentially useful document as someone is designing a study or planning to download data and use that as well. So I'm going to now jump into a bunch of examples from these different study planning during after acquisition sections. So any questions before that? Okay. So for study planning, and by the way, I'll mention the talk I gave you a few weeks ago on fMRI beginning to end also included some QC stuff in it. So if anyone wasn't here, you could also go back and look at that as well. But for study planning, I think a big question is what measures matter for my study? Where do I want brain coverage, distortion, temporal signal to noise are good enough? How do I, if I'm doing connectivity, what do I call stable or not? And how do I avoid problematic artifacts? And again, problematic contextual term. There are some artifacts that are always problematic, and there are some artifacts that might be problematic in one study and not another. For example, this picture to the right is an average of what voxels have data across a study of, I think, 30 people. And yellow means all 30 people have data in that voxel. And if you look at the bottom here, there's a bunch of voxels that only some of the subjects have data, and some of the voxels which no subjects have data. If this is, and this is primarily temporal lobe, and maybe, I think if you go more forward, it might be some inferior, occipital frontal lobe. If your study does not care about the inferior temporal lobe and does not care about orbital frontal cortex, these data are great. If your study does care about those areas, you should not be using these data. And this is especially true with downloading. So like, let's say this data set was collected from someone who did not care about these areas. They published it, it's great, they were happy with the data. If you're now downloading this data and using it for something else, and you care about those areas, you gotta, there's things you care about the data and you gotta pay attention to. As you're planning your study, putting together your operational procedures of how you're doing everything, what to document, what to check in real time, and what data and meta or peripheral data to share, and also how. I think just in general with documenting, we talk a lot about data sharing in the field, but the most important person you're sharing data with is your future self. So I think there's a lot of effort in saying, like, let's make something as rigorous and consistent across 1,000 studies so computers could scrape it. And sometimes that becomes so hard that people just don't bother. But at least getting to the point where you're saying, I've stored the stuff that if I have to look at this data 5 years from now, I've stored enough information that I know what the heck I did, is, I think, a very realistic and very good goal for when you're thinking through operational procedures of what you need to share. And finally, piloting and so as you're doing the piloting phase of a study, testing your quality, it should include tests of your quality control measures and tests of your operational procedures. I have a bit more in that previous talk on July 7th. I have a bit more about piloting and quality assurance. A few more pictures there. So study planning, operational procedures. So these do a few things. These could be a list or a checklist, and they should include procedures on what you're logging in when, like I just said. And these are a few things. These are primarily, it makes you think in advance what you need. And second, it reduces errors. There's a large literature on the benefits of checklists. Because even if it's something cold, if, in an MRI study, there's especially with the acquisition, there's a thousand little steps. And if you forgot to press the button to shim, or you forgot to you ran your localizer a little bit differently, or you forgot to turn on the microphone before you started the scan, these are all things that happen. These are all things that have happened to me. And probably anyone else who has scanned significantly, you're going to forget things. So the more you can sort of give yourself a script to do, even if you don't have to stare at the script, before every step, it's just sort of that reminder as you're going through it. It really helps. So, like I said, I'm using all the stuff the study Catherine is ongoing collection. This is an example of her operational procedures. So she has a document with some pictures to remind herself, this is how the connections look. This is what you have to connect in. We use the HDMI input, even though some people might switch it to something else on the scanner. Remember, there's 2 cords you have to plug in. Here's the steps to start scheduling the patient. As depending where you are in the practice, some of this might be, register a patient and you don't have to write 10 lines. But if you're new to scanning, or you're new to a scanner interface that you scan the one scanner and you do another, sometimes this much detail is very useful. And then how to set up your imaging acquisition to make sure it's consistent every time. So which parameters to connecting pictures. So this is your document for yourself. You can share some of it the data, but this is really the thing that helps you know that you're doing things correctly. So one example from Catherine's study is, as she was piloting, she was showing some failures in structural alignment. So to the left, we have the fMRI volume, and to the right, we have the anatomical volume and the fMRI volume aligned to it. And when she was first piloting her data, it turned out that this was failing miserably, most likely because the fat on the side of the head is really bright, and this is called invalidity. So we're seeing some brightness here, and that was just messing things up. It was solvable with some tweaks in how the alignment was done, just some parameter tweaks. But it's something that, there are scenarios where you see this and it turns out there's something wrong with your acquisition. In this case, yeah, it was solvable on the software side. But if it turned out that there was something wrong with alignment that was acquisition, you want to find that out as soon as possible. And that's why sort of running your full pipeline in the pilot stage is essential. So for study planning, again, this is, the script to actually analyze the data. The maps were just looking wrong. And what it ended up being is, by looking at the time series of the data and the pattern of activation for this localizer task, so that the faces, fixation, object, scene files, it just, you squint at this, you see oh, maybe it's following here, maybe it's following these blocks, but this is not what we expected in the diffuser gyrus, which should be one of the most robust areas to this. And after investigating a bit, it turned out that the wrong one is being pulled into the script. And when you use the right one, it looks like this. So this was an early step of quality checking the actual processing pipeline and realizing there was a bug in fixing it. So I'm now switching to, this is an example that kind of jumps from study planning to this soon after acquisition. And this is looking for distortions and dropout that might affect localization alignment. So I pulled back those HCP data from earlier in the talk. And just to be clear, the brain does not look like this. This is really impressive distortion. And this distortion, like we said, you can correct for a lot of distortion in post-processing. But it's hard. It's harder, and you have to make sure that everything is tuned correctly. So you really want to look at it, and if it's distorted, you really have to check that it actually did align correctly. And again, there's some studies where a bit of distortion doesn't really matter. Like, in this study, like let's say your research interest is primary visual cortex and the rest of the brain is just whatever, you got it. Visual cortex actually looks real. Actually, this might be too low. I'm not sure. Like I said earlier, there's no gyri here, so I have no clue what slices it is. But let's say you're interested in this posterior area. There's not as much distortion. You can probably be pretty confident what you're getting. So that's good. If you're interested in something here, you better make sure that your distortion correction and alignment are done correctly. So now, as you're acquiring data, it's important to check outputs as soon as possible. And that's your neuroimaging, your peripheral measures, and your behavior. This is so on the GE scanners, we have the AFNI real-time interface, which as you collect data, it can show you your fMRI appearing volume by volume, and it can show you your time series, and it shows you your motion parameters. So this is like as you're scanning, and then as you're going, the person moved their head a lot. And there's two things you can do with this. If the, in some cases, this might end up being garbage data if they're moving their head that much frequently. But this immediately says, after the scan or stop the scan and say, you're moving your head a lot, can we help you? Or is there something wrong? Because if it's one run like this, you can help them improve for the future runs. If you've collected the entire data set without noticing this, you've just wasted your time, their time, and resources. So this is, checking motion, looking at your data in real time can be extremely useful. And just in general, documenting anything atypical. This is the other advantage, the other benefit of making a data acquisition protocol, like some sort of checklist or plan, because then you have it, you say this is what's supposed to happen, and then you know very clearly every time something happened that's not there, you know what to write down. And that can be extremely useful. And that's, I just made some things. You had a plan of what run order you did, you had to change it for some reason, there was a bad run, like this person moved. I had a data set where the headphones had noise cancellation that flickered in and out in some subjects, so I documented that. Or if as you're collecting, you see any artifacts or other issues in the data that you want to follow up with later. So in this real-time monitoring, you're also wanting to make sure things work the way they're supposed to. So again, from Catherine's study, she used PsychoPy to present stimuli. And she made sure in the PsychoPy script, it's logging the key press key is the signal from the scanner saying a new volume is being corrected. So it's logging every volume that's corrected. And in a good run, it's waiting for the scanner to start. And then it receives one note from the scanner saying the scan has started, and then the script starts. In this other subject, it's waiting for the scanner to start. And for some reason, it took 3 volumes. Three volume collections before the scanner to start. So all in all, if this is the only issue here, this is not a big deal, except now that we're processing that data, you've got to know that everything is happening 2 seconds later than planned. And that's a big deal. So if you didn't log this and you didn't know that every event in your scan is 2 seconds later, depending on your task design, that can make a really big mess. And this is another good example of like what you want to monitor. So this is subject behavior. In the task, there was 2 cue stimuli appeared, fixation, they're told to monitor the thing above. You remember the thing above, you wait, you show them the thing above, and they have to respond. And there's this little box here that has a green light go on whenever they press a button. So you can sort of see when they press buttons as the scan is going on. And that's how things should be. And there was one subject that instead of pressing the button when the target appeared, they were pressing the button at other times during the scan. And it turned out this volunteer just misunderstood the task. And while the scan was happening, it became clear that was happening. And they were able to identify the only way that this would be known is by looking at the button presses during the scan. I guess if there was a summary log right after the scan, which I think you have also, I have this in front of me. You could have also looked at that and said, hey, they got every trial wrong. But you actually have to be monitoring that. If you're just collecting the logs and saying, I'll look at it later, that's not going to help you. And the important thing with this is, number one, it says, okay, we got to make sure they know the task can be collect data. So you just saved resources and save time and save effort. The other thing is when one subject makes a mistake, that's not necessarily their fault, that's your fault, because you did not explain it. So by noticing the subject was confused, Catherine changed the protocol to say, let's make sure they have a practice phase before we start collecting data. I observe them and make sure they understand what they're doing. And that's type of mistake we all make. And by monitoring and realizing it was happening and that there's a problem, it was possible to go back and fix it early in the process, not after you've found 5 more subjects that didn't understand the task. Other things to collect during data acquisition. This is sort of just like I was saying, like collecting the anomalies. So this is an example. Often, at least when I do this, I'm either typing on a side computer or taking things by hand and then typing it in later. These are your scans, 1 through 10. Localizer scan. These are different tasks. And like, ooh, run 1. They were moving around a lot. Scanner crashed. Had to redo. Cardiac data looked weird. They're moving again. They're moving again. And then, they shifted their head a lot between when this run ended and this one began. So these are, again, the things that sometimes you can tell post hoc by looking at the data. And some of this stuff, if we didn't take notes, we would have lost. So it's important to sort of keep track of that stuff as we go. Here's another example, like that localizer scan. It shouldn't look like this. This is, obviously it should look kind of like a slice of a brain, not like snow. And in this case, immediately saw it, said, that's bad, rebooted the scanner, and it worked. So whatever caused this issue, we don't know. But it was another quick, something looks wrong before, instead of driving forward, let's take a step back and try and fix it. We can also do real-time monitoring peripheral measures. This is both good in acquisition. I could have also probably put this in the soon after acquisition phase as well. One thing I sort of put on my slide earlier we didn't mention is I tried to define studies in different phases, but they all interact. So like pretty much everything I'm saying during acquisition, we kind of do more carefully after acquisition. And there's some stuff I'm putting in after acquisition that sometimes ends up doing a little bit during, and then there's processing. So like everything melds around a bit, but there are these different phases of the study that they're still useful to sort of parse things into. So we like to collect cardiac and respiratory traces during data. I mentioned that also in my July 7th talk. This is an example of a cardiac trace. It's run after these program physiocalc.py. I wanted to also highlight that when you run this program, it gives you a report and an interactive screen that looks like this, that shows you the trace, which is this line going up and down every cardiac pulse, and where it says all the peaks happen. And there's this nice convenient coloring on top, which says relatively how much is that beat to beat heart rate changing. So like if the beat to beat heart rate is, if there's less gap between beats, it becomes bluer. And if there's a wider gap, it's redder. So that those colorings are very nice because it gives, we expect some variation in heart rate, but if you see something like, a really dense area of blue, that might be a sign that something's going on there. That's wrong. But just as one example, this is, when you're designing software and you're putting tools together, having the QC stuff built in can be extremely useful. So I've, this is an example from AFNI, but I also try to take it apart with some of the software I'm developing. But this is what it should look like. So you have every beat. There's a little triangle here saying this is when the heart was beating. And you can see that the program mostly automatically detected all of them. Maybe if I look here, I grumble and say, man, they might have added another peak there, but it looks pretty good. And then we can correct the ones that are wrong. This is one of the runs from this. So this was a good run from her study. This is a bad run from the study. And what you can see is very often with these pulse oximeters on people's fingers, if you wiggle your finger, you're just totally messing up the data. So there's different ways to like make sure they don't wiggle their finger and get the pulse oximeter on them well. But if they are just moving their hand around the whole time, your data, the data is garbage. So if you're looking here, there's actually a decent stretch from here to here that looks okay. I think after failed, I think because there's these other things that just totally messed up the metric they did for peak detection, because I think it sort of does like an average of what the peak height should be. But every one of these is a finger wiggle that's just garbage data. So this is an example of a data that just was probably unusable for a large chunk of this run. Any questions so far? Right, today. If you're now, soon after acquisition, you can kind of continue some of these visual checks. And the reason I'm stressing soon after acquisition is because there are some things you might find in close analysis that are going to affect your future scans. So like, you piloted, you thought you were getting areas that were interested in, but when you start collecting for real, something's wrong. And you want to, so you really want to take at least some look at the data soon after acquisition. The other good reason to do things, to start looking at your data carefully right after acquisition is that's actually when you remember the scan. So if something looks weird, you're like, oh yeah, that happened on scan 4 and I forgot to document it. So it helps you put those together. Yeah, I think there was a I'll keep the guilty names unknown, but there was a very large study collected at some point where they were really interested in one subcortical brain area. And it turned out after collecting a lot of data, they really weren't getting that brain area with good signal in a non-trivial number of their volunteers. And that data was not usable for the one of the main goals of the study. If they analyzed it carefully and QC'd it carefully earlier, they would have noticed and they could have changed the parameter. There was also a study years ago where the field of view parameter is how wide you image it. And instead of doing a field view of, I think, 240 millimeters, which is the width of your brain, they actually did a field of view of 240 centimeters. And what that meant is their data was essentially, their brain was like 1 or 2 voxels in the center of the image. And this, I actually don't know who they were because it was even before I got here. But they did not look at their data until they collected a non-trivial amount. And there was really nothing you can do at that point, unless you're doing single voxel whole brain analysis. So this is just an example of the types of things you look for. This is an anatomical image. You can see that the tip of the nose is wrapping around in the back of the image. And I think this is a nice visualization of a wraparound effect. In this case, this one is really minor. You might have to tweak a few parameters to remove the skull to get to the brain, but otherwise this is addressable. But if something wraps around so much that like the brain loops in itself, or there's aliasing, which is sort of another type of wraparound, where some parts of the brain sort of fold over in themselves to other parts, that's a serious issue. But again, it's contextual. So like if 2 areas are wrapping over each other and you're not actually those aren't areas that are the focus of your study, it might still be okay. But it's something to look for, like how data wraps around. Another thing that's soon after acquisition, just making sure the data you thought is actually present. So this was a script Catherine wrote that as she was collecting more and more data, I wanted to keep track of what was there. She just sort of wrote a superscript that was, okay, I have 5 subjects. Each subject should have these runs from these 2 sessions, and these things are processed. So instead of sort of doing it as script by subject, it just runs the script and says, oh, these are sessions that don't seem to exist yet. These are data that haven't been processed yet in the subject. These are regions of interest where I thought I should have data, and it's saying I don't have enough data in these regions of interest. So it was one script to sort of pull a bunch of this information together to highlight if any of these issues are happening. The other thing to look for is just genuine human anatomical variability. So this is a map of a face minus baseline contrast. You can see It's mostly bilateral. We got a lot of activation on both sides of the brain. This is fairly typical. There was one volunteer in the study that had atypical anatomy. So you can see that this person's brain is very asymmetric. And areas are just a completely different shape than what we'd expect. And if you look at that face minus baseline contrast, you can see it's really in an anatomically distinct area. And just to be clear, incidental findings like this are very common. The number, I was trying to find the exact paper, but the number that's often thrown around is about 7%. So if you're scanning, you're going to see something which is considered atypical in about 7% of the healthy volunteers you scan. That's an old number, so it might have changed a little bit, but anyone who does significant scanning will find things atypical. Most of the time, atypical is not concerning. It is just, this is how the scientific community thinks the brain should look, and this brain looks a little bit different. So most of the time it's not concerning, but things like this are reasonably frequent. The thing to keep in mind here is, for Catherine's study, all her analyses are within subject with regions of interest that are defined per subject. So a volunteer with a really atypically shaped brain is, as long as everything else looks good, as it was in this case, is actually not a problem at all. But if this was an analysis where you're supposed to align every participant to the same anatomical template, and you think your gyri and sulci line up to match this, to represent the same underlying cortical areas, this could be a significant problem. This volunteer might not be usable in a study where you're aligning to a template while this volunteer is perfectly fine for the study here. Any questions so far? Another thing to look for is, like I kind of mentioned this earlier with that large N study. If you have critical areas of your study, are you getting your data there? So in Catherine's study, to get a high spatial and reasonably high spatial temporal resolutions, reasonably high spatial resolution and slightly higher temporal resolution, she was not collecting the whole brain. She was collecting a slab. And she is particularly interested in hippocampus MTL, which is down here. And what you can see is there's some areas that are right near the edge of that slab. So if the person is moving their head, some voxels of potential interest might not have data the whole time. So it's really important to identify those voxels and check how many you lost, and make sure that not too many were lost. And obviously some were lost, but if it was substantial in multiple subjects, then maybe, okay, we have to rethink, what is our field of view? What is our slab? What do we do here? But in this case, it's so far been a reasonable thing, but you still want to make sure you're not analyzing data where you don't have the data you think you do. The other thing for Catherine's study was, we're looking at, like I said, hippocampus MTL, and want to segment these into different portions. So like the segmented map is down here. This is a reasonably good segmented map. These are 2 slices in a volunteer. These are made based on 2 images, a T2 weighted anatomical and a T1 weighted anatomical. And you can see, nice gray-white contrast here. It's a little bit harder to see here, but you also have decent, there is some contrast in the T2 as well. And then there was another volunteer where, if you look, especially if it's easier for me to visualize in the T1, you can see just a little bit fuzzier. And this also just has a little bit less contrast here. And the segmentation program just plain failed. So it gave RIs, but this is not hippocampus MTL. This is just, I don't know what to call that. Wrong. That is wrong. And it turned out that, with, again, tweaking some parameters, it was possible to get the, better RIs from this data without having to recollect these anatomical scans. But you have to look at the data and see this is happening. Like, if you didn't bother looking, you said, oh, I got an anterior hippocampus RI and it says it has 30 voxels and all is good. If you didn't step back and look at it, this could be missed. So just sort of in general, I've covered some of this, but like I said, we started with pilot scans, and when you finish your piloting, like I think I'm getting data that I should get. That also gives you a benchmark. So as you're collecting data for the actual study, you could say my TSNR was 100 in my pilot. This subject has a TSNR of 50. There's something going on here. My alignments, my distortion, my motion is different. So always check back to those pilots. And always check the study goals. Is it hitting a brain region of interest, or there's no artifacts? So I'm going to show a bunch of examples with AFNI's Instacore through this talk, but this is just one example of an Instacore artifact. So Instacore is a tool in AFNI which lets you you load up your data in AFNI, and you can sort of click on any voxel and say, give me the correlation between this time series and every other time series. And you can just sort of move around the brain and see how the correlation now changes. And this turns out to be very useful to explore your data and understand patterns. So this is one of the first cases where they got good use of Instacore, where they clicked up here, and you see it's a really bright correlation to the stuff right around it, and it kind of gets less correlated far away. It doesn't follow anatomy. So usually when you're looking at correlations, maybe we see some bilateral symmetry, maybe we see something follow a gyrus a bit more than jumping between gyri. But this is just kind of sort of a blob at a coil. And it turned out in this case that one of the MRI receiver coils was flaky. And you can see that the data was collecting, and that receiver coil went, something's, let me stop working for a little bit and then go back up. So this is what was being correlated. Like it was kind of flat, had a giant drop when the coil flaked out and then came back up. And that's what this correlation was showing. It highlighted a artifact, actually a scanner problem that I think the receiver coil had to get replaced or fixed. Here's another Instacore example from Catherine's study. And if you look at it, first thing you see this, you're doing a correlation here, and you're kind of seeing these curved waves through the data. It is concerning. It would be more concerning if these were areas within her primary regions of interest. The time series, we're not seeing any huge jumps. And then after pre-processing, it turned out that most of this artifact, so after you've moved motion, did some censoring, did some other stuff, this artifact wasn't as prominent. So the decision was made that this actually isn't that concerning. But it involved checking an investigation and logging. So like maybe in the future, like, oh wait, what happened there? Maybe we have to go back to this. So the other thing to check during processing is just that the scripts ran appropriately. So if you run, so AFNI's super program is called AFNI-Proc. It sends out a giant log of everything that was running every message. So always check that if there's warnings or errors in it. But as part of running, Catherine also created a script that sort of pulled out key information. This is the data that we're using. This is where it's from. These are where the event files are from. This is how many trials we have. So if anything weird pops up here, it's good to see. And this is also good for just logging, because it says, I am looking at these images. Where are these images from? I have a file that says I loaded these volumes to make this image. So it gives you sort of your own memory. It builds up your own memory as well as a future check. So you could also look at where do you have good data. This was an example of a free surfer segmentation. So free surfer is a program to segment the cortex of the brain in different ways. And for whatever reason, when free surfer was first run with the default parameters, it just kind of forgot about half a one of the temporal lobes. And I'm pretty sure this was also fixable, but it's, you would only know if you looked. And this is again that image I showed from earlier on, but as you're doing your full processing, getting that coverage map from your full study is useful, because I think there's a lot of studies, especially with connectivity, where you're saying, hey, this region of interest seems to show some variation across my population, or it's telling something different between two populations. And it turns out that like in one group of people, you have data here, and in one group of people, you don't. And that's gonna, especially when you're talking about ROI analyses where you're averaging. If you're averaging literally different voxels, you're averaging different parts of the brain. So you could call two things a front, inferior temporal region of interest, but they might have different physical parts of the brain in them, and that's going to affect what you're measuring. So if a region of interest is covering different parts of the brain in different subjects, that's good to know. We can also check head motion and censoring. I'll note this picture is from when you run AFNI, it gives you an interactive report with a lot of images. A bunch of the images, some of the images I've already shown, a bunch of the images going forward are from that report. I think it's a really important because, like I said earlier, quality assurance involves manual work. Like you really got to look at things. It's not just a bunch of numbers on a screen. There's not, because some of this stuff just doesn't have summary metrics. But even with those numbers, like the more you can make the key information visible to people, the better. So the AFNI report is one tool of saying, here's 20 things we think are good to look at all in one place. So having these automatic tools, these automatic summary metrics are good. So this is an example of head motion, and the red areas are areas that were either censored due to head motion or some other artifact in the data as part of the automatic processing pipeline. And in this case, 26% of the volumes are lost. So, if it's 10%, then you can say, okay, it's a gray area where those 10% something is. At 26%, it's probably still a gray area depending on what you're doing, but it's much more on the, I don't think this data could, I'd skew much more towards this might not be useful data. But a lot depends on where these are, how much data you have in total. And all that stuff. Like, for example, a lot of people doing scans in children or infants, they know they're going to get a massive amount of head motion. So they might collect 3 times as much data, say, yeah, we're going to lose a quarter of our data, but we're still going to get enough data. So there's no like percentage cutoff, but it really is, again, context dependent on what you collected and what you kept in mind. Other things to look at, this is also from the AFNI reports. This is actually from the not from Catherine's data, but the other paper is listing. You can have a stat map of your contrast. So you can see kind of gray area blobs. And if you knew what task this was, I would say, hey, this looks reasonable. You can correlate to essentially make a region of interest of white matter and say how much does that correlate to gray matter. And you can see like just some correlation, but it has some anatomical structure. It doesn't look ridiculous. So this is a good subject. This is a bad subject. So same task, same everything. You can see the white matter massively correlates with gray matter, and you can see that there's really no blobs, and there's in some ways there's actually more activity outside the brain than inside the brain. So this is an example of a subject that, so there was essentially they were rocking their head to the casket bit in this case, and that just messed everything up. So it might have been a little bit more subtle in the data, but you look at this map and you say, okay, there's something really wrong here. Again, you could do manual checks with Instacore. Here's an example of one data set where you did Instacore here, and you kind of see these waves of lines through the image. And it turned out that there's a lot of head motion. So the black is the time series are correlating, and the red is the head motion. And you can see there was a big jump, a big movement of the head that appeared in this voxel, and we kind of get this artifact here. So this, might be just corrected by censoring these volumes, but it's something to be aware of. And here's an example of, if you look on this image, there's this big black dot in the center of the brain here. Don't know if that's just normal anatomical variability or something else. So we definitely see the this is like fourth ventricle sister that looks a little bit bigger. And then when you did Instagram correlations, you could see most of that is also in the CSF fluid. So it's mostly contained to that area. So it wasn't of a huge concern unless it's right near areas that you were specifically caring about. Other metrics they have, again, this is, for resting state data, correlation to posterior cingulate. Do we get a default mode network? Correlation to white matter. This is sort of like everything's correlated to things near it. And these are these epivariance lines where you're seeing, are there these vertical lines where something seems a little bit off? And this is a study that looks pretty good. Again, we see structure. Things are mostly following gyri. I did some Instagram inspection of this, but it was otherwise good. Here's the intermediate subject, which just doesn't quite look as clean there. Honestly, if I was collecting data, I set my standards higher, I might have rejected this, but this was actually pretty typical for this data set. So I'm like, whatever the authors are happy with, I'm saying this is acceptable. And here's one that was just high motion and bad maps, otherwise disaster. One other thing to check is alignment. So what these images are showing is the underlay is the fMRI EPI volume, and the red line is the borders of the anatomical structure. And what you could see here is, so if you're looking at alignment, do the edges match? Do the gyri match? And I look at this and I'm like, that's kind of okay. But in apnea, there's a way, because there's a lot of people who have issues with left-right flipping, and this has popped up more and more. Actually, it's hopefully popping up less, but it used to happen a lot. We flip the EPI and say, does it line up better? And now you can see how well this lined up. So like all these red lines really follow the EPI structure. So it's a really good alignment in this case. And this is an example of an image that's flipped. And I'll note, if you have this flipping and you can't figure out what the truth is, the data is garbage. Because, it could be the anatomical that was flipped left right. It could be the fMRI that was flipped left right. If you don't have any records of which was which, you don't know what the left and right of the brain are. And here's another subject where if you look at it, neither really lined up well either flipping. It's kind of missing the boundaries. And I like and dislike an example because this is why you really have to also quality check your actual pipeline. So this paper I'm showing was a paper where I'm demonstrating proper quality control metrics. And it turned out that in my script, I accidentally was aligning the fMRI data to the wrong anatomicals of other subjects. And neither was lining up well. And we actually made it through first review before realizing this problem. So it would have been great to have a mistake this large in a published paper on quality checking, but we caught it in time before publication. And I have the whole story of how it happened online. If you're bored, I can point you to it at some point. But it turns out that, this is like if I looked at it carefully, I was like, no, neither of these are good. There's something really wrong going on. I think in the original version of the paper, I just said the alignment is failing. So I knew it was bad, but I said there's something wrong with alignment. But I didn't realize what was wrong is I was aligning the wrong brain. What was interesting is there's a cost metric that comes out with these alignments. And normally that cost metric is just a relative value. But it turned out that if you look across the whole study, if I did the correct data, this was the range of values for that cost function. And with the wrong data, they were actually this totally different values. They were much lower. The cost function was just a totally different value. So it's a relative measure, and it just points to this cost function that we just kind of thought was, you're sort of you're finding a local minimum. But it turns out that if your acquisitions are the same, that local minimum actually has a meaning, and we could use it as a potential quality measure of across the data set of, hey, the local minimum on these five subjects are lower. What's going on there? And I'll say quality assurance research continues. In my multi-echo talk, I mentioned this P-bold or probability bold method that Javier I and others developed. You can go back to that talk for a little bit or look at the paper. There's also a brand new paper by Charles Lynch that is using assumptions of what network connectivity patterns should look like to make a quality assessment measure that could automatically be calculated on large data sets. So this stuff is still ongoing, and there's research still going into these areas. So again, these are the take-home messages I started with. You really got to know your data and understand what is good data. Quality assurance protocols are important and essential to an understanding. And automation is great. So I showed you almost every image I showed you was automatically generated in this talk, not all, most. But you have to actually look at them and understand them and think about them, and sometimes dig a bit deeper. And this involves training and learning. Now, my part 2 take home is it really starts early with study planning and doing every step of the study. And I would say this includes it, especially for data collected by others, because unfortunately, very few people share data with quality reports. So you just kind of have to check a lot of it yourself, and break that trend. If you're doing it and you're doing quality check and you're sharing data, share your quality check procedures and reports with the data you're sharing. And yeah, like I said, the human parts, automated is important, but human observations are essential. Especially as you get to bigger studies, the question is, we have finite human time and computer time is much more broad. So how do we optimize the use of human time? And I think that's actually a big area of both thinking and research in study design. And quality assurance is not just keep versus exclude, it's what questions can I answer with these data? And yeah, there's more research and it could be more active. So that's it. Any questions? Okay, really quiet group today. Let me double check that there's no online questions. Chat here. Oh, looks good. Okay, thank you very much.